Sí, yo comienzo. A ver, si Justino ya termina ya. Justino, hola, buena tarde. Bueno, que eso.
Ya te regañaron.
Voy a presentar a Enric, todos lo conocemos, pero tengo que presentarlo, que es licenciado, se licenció en Ciencias del Mar. Aprobaste, ¿no? Todo, ¿no? Sí.
Aquí estoy, sí.
En las Palmas de Gran Canaria. Y después de hacer aquí en el instituto la tesis doctoral y después de hacer un postdoc en scripts, ¿no? Pues acabó en México, en el CISESE, donde ya lleva 10 años, ¿no? Trabajando con datos experimentales y tiene una flotilla bastante importante de gliders, y es lo que nos va a presentar hoy. Pues bienvenido, muchas gracias por venir de vuelta a casa. Y te escuchamos con ansiedad.
Ok. ¿Voy a dar la charla en inglés o en qué lengua quieren que la dé? ¿En inglés? ¿Sí? Vale, muy bien. Vale, pues hello to everyone and thank you very much for being here on this Friday's talk on Wednesday, but yeah, it's called a Friday's talk. And well, my name is Enric Pallàs-Sanz, as Álvaro said before. I'm coming from the Department of Physical Oceanography in CICESE. It's the Centro de Investigación Científica y Educación Superior de Ensenada, Baja California. And today I'm going to talk about some relevant observations that we have collected during the last 3.5 years in the Gulf of Mexico, mostly in the western Gulf of Mexico. So I'm going to talk about phenomenology, I like this word, some processes at mesoscale and submesoscale. And what is our main platform for measuring? It's the Seagliders. It's the Seagliders. The Seagliders are built by the University of Washington, and right now they are commercialized by Hydroid. It's Huntington Ingalls Industries. It's the new provider of this kind of gliders. And typically, it's an underwater vehicle that works with changes on buoyancy. So they have a reservoir with oil. Then when the reservoir gets filled with oil, the glider gains floatability or buoyancy, sorry, and then surfaces. And when the oil gets out from the reservoir, then gains height and then do a dive into the water column. So the trajectory through the water column, it's a zigzag trajectory. It takes about 5 hours going down to 1,000-meter depth and surfacing at surface. No? And the horizontal resolution that we get, it's about 5 kilometers on the horizontal. So it's a pretty high resolution of the profiling. The glider typically it's mounted with 2 sensors, the Seabird City Sail, that it's a free flow conductivity temperature depth sensor at pretty high resolution, vertical resolution of 0.51 meter depth. And also we have this wet labs triplet that it's a optical sensor, and we get fluorescence and backscatter, and we get colored dissolved organic matter, CDOM. So today I'm going to talk pretty much about observations on conductivity, salinity, temperature density, and some observations also of chlorophyll. Where we operate all this fleet of gliders, it's, well, first I'm going to show where we operate them. It's in the western Gulf of Mexico. We see on the left side this spaghetti plot with all the trajectories. It's 19 missions. Here it's the time schedule of these missions from summer 2016 to December 2019. Pretty much we've been measuring this property or essential oceanic variables for 3.5 years in a continuous way, more or less. On the bottom, I show some statistics of the missions. On the x-axis, it's the number of missions. Left plot, it's the number of dives. Middle plot, it's the number of days. And the plot on the right side, it's the distance traveled. Pretty much we get around 400 dives. It's 800 profiles. Every dive are 2 profiles. We are out on the sea about 100 days per mission, and and we travel distances around 1,200, 1,400 kilometers as long with the glider. So this emphasizes the strong regional monitoring of that we can do with gliders. Gliders are not convenient for very long missions because the batteries, we have this limitation. So what's our region of study? This is a video of absolute dynamic topography. Red colors are anticyclonic anomalies or anticyclonic eddies because it's high sea surface height, and the green colors indicate low absolute dynamic topography and are related to cyclonic circulation. So red, anticyclonic eddies, green, cyclonic eddies. What we see, it's a very strong forcing by this Yucatan current getting between Yucatan and Cuba, and this current gets out of the Gulf of Mexico through the Florida Channel. So this is the main forcing on the circulation of the Gulf of Mexico. It's the loop current system. This loop current system often liberates or shed some large anticyclonic eddies that propagate westwards because the sphericity of the planet, or the beta plane, they propagate westwards at 4 kilometers per day, 7 kilometers per day, and and they transport waters from the Caribbean with Caribbean signal to the Western Gulf of Mexico. Other features interesting in this movie are the cyclonic eddies. We see small cyclonic eddies that are generated north of the Yucatan Channel and propagate on the edges of the loop current. These are called loop current frontal eddies that are cyclonic eddies. And these ones, there are small cyclonic eddies that are generated and then propagate around the loop current. These are very important on processes like the shedding of these large loop current eddies. So this is pretty much the circulation in the Gulf of Mexico, and we see that it's dominated by cyclonic and anticyclonic circulation. No, it's like a turbulent mesoscale basin. And if you saw that I superimposed all the missions there were the trajectories, so you can collocate the position of the eddy, respect the trajectory of the glider. We pretty much have the mission to cross these large structures and to monitor the properties inside these eddies. So first thing I want to show is the water masses in the Gulf of Mexico. I'm showing the TS diagram for the 18 missions, and they are colored. Well, each color indicates one mission. So we found consistently these water masses, the Caribbean surface water, that it's above 22 degrees. It's a surface water with a lot of variability and with the signal of freshwater filaments. All these lines indicate freshwater filaments with low salinity and different temperatures depending on the season of the year. We have filaments called freshwater filaments all the year, and systematically we cross these structures with the gliders. What that means is that there are ubiquitous in the Gulf of Mexico. They grab around the eddies and they are transported offshore with the eddies from the coast offshore. And other water masses, the most important water mass is this water mass from the Caribbean. It's the subtropical underwater that has a very strong signal of subsurface salinity. It's very salty water. And this water, when it's eroded and the salinity it's reduced, it becomes what we call the Gulf Common Water. Gulf Common Water is the water that typically is in the Gulf of Mexico, but this water is formed through the transformation of this Caribbean water. In the bottom, we have the typical Atlantic Central water and the Antarctic Intermediate water, so at below 300-meter depth. So these are the main water masses that we find. What's the structure, the vertical structure of a loop current eddy? we did this section. These are the contours of the eddy, and this is the trajectory. So we see that we crossed the eddy. The eddy was propagating southward, and we tried to cross it because the glider is very slow platform, and sometimes we have a lack of synopticity, very strong lack of synopticity, because the eddy moves and the glider moves, and both structures move each other. So sometimes we overestimate the horizontal gradients, and sometimes we underestimate the horizontal gradient, depending on the structure it's moving toward the glider, or the glider and the structure are moving towards the same direction, no? Depending on that. So what we see, the loop current eddies are very strong warm anomalies, 9 degrees of temperature anomaly, it's huge. And we have also 1 PSU of salinity anomaly. So this huge heat and salt content that is removed from the Caribbean, it's transported towards the western Gulf of Mexico, and at some point it's gonna be released on the surrounding waters. If we release all this heat and salt content in the upper 1,000 meters of the Gulf of Mexico, the Gulf of Mexico will increase by 0.023 PSU and 0.24 degrees. It's pretty significant increase of temperature. And to compensate this increase of temperature and salinity, we need 1 year by the heat and the riverine fluxes in the Gulf of Mexico to compensate this increase of salinity and temperature. So there are very important structures in the salt and heat budget in the Gulf of Mexico. These eddies have pretty much subtropical underwater, a very strong subsurface salinity maximum. So what happens with this subtropical underwater inside these loop current eddies? The loop current eddies trap water from the Caribbean, very salty. This is the mission 3, when the loop current eddy Poseidon, well, we put names to the eddies, and this one was called Poseidon. So when Poseidon was young, mission 3, we see a very strong salinity core here, above 36.8 of PSU. And with time, mission 4, it's winter, mission 5, it's spring 2017, and then we get to summer 2017. So the time series go from summer 2016 to summer 2017, and what we see is that the loop current eddy Poseidon has an erosion, an important erosion of the subsurface salinity maximum with time, and we see that the maximum is shallower when the eddy is older. So this is also emphasized here in these TS diagrams per each mission. Mission 4, strong salinity maximum, and it is eroded as the time pass. No? So this figure on the bottom shows this decay of the eddy with time, kinetic energy, eddy kinetic energy, young eddy with large eddy kinetic energy, and how it decreases with time as it's being eroded. So what's the physical mechanism of this erosion and transformation of subtropical underwater to Gulf common water? The main physical mechanism, we believe, it's the winter convection. So the black line in this bottom plot indicates the winds above 10 meters of the sea surface, and we see that there is strong events of wind during winter. So this erosion of the salinity maximum is related to winter. So to show that, we have measured the regions where we can find unstable water column with Brun-Väisälä, square Brun-Väisälä, negative square Brun-Väisälä. So I indicate with red colors the regions gravitationally unstable. And we can see clearly it's the same time series. It's Poseidon, young Poseidon, old Poseidon, and shallow mix layer in summer, and deep mix layer in winter, about 150 meters. So this deepening of the mix layer is clearly related to these events of winter convection. So, so there is a very clear seasonal trend of gravitational instabilities that they can reach in winter 70% of the water column is unstable to gravitational instabilities. So we believe that this is the physical mechanism that erode this subtropical underwater and transform to Gulf common water. Okay, we don't have only these large loop current eddies. We also found smaller eddies. Here it's very nice observations. This is the same section of loop current eddy Poseidon. And in this plot on the right, I'm showing stratification, square Brumbaisala. We see two thermoclines, well, two pycnoclines, the seasonal pycnocline in summer at 40 meters, and we have the main thermocline of the eddy. This is the thermostat, or the pycnostat they call. And what we can see these anomalies, we can see these circles of low potential vorticity and low stratification bounded by high regions of higher stratification. So this is very, well, we can see it better in these vertical profiles. Red lines are the vertical profile of Brumbaisala, square Brumbaisala inside these eddies, these intra-thermocline eddies, and the blue line is the background stratification. So we see that these eddies are low stratified eddies, and they are bounded by high stratification above and below. And this is because the isopycnals, obviously, in an intra-thermocline eddy, anticyclonic, they expand within the eddy and they shrink above and below. So we have strong stratification above and below, and low stratification or potential vorticity in the middle. These eddies rotate anticyclonically and orbit around the large one. So this is very interesting, that are orbiting around the large eddy, like the moon, no? It's orbiting around the Earth. So these small eddies are orbiting anticyclonically and are translating around the large eddy. And they contain subtropical underwater. So they form near the surface, and somewhat they have to subduct. Vertical velocities are around 0.2 meters per second, and an anticyclonic circulation. This is the geostrophic velocity computed from the density gradients. So these eddies are pretty interesting. They are all the time, we found them many times with the gliders, and we don't know still what is the mechanism that they generate. So we are investigating on this. What other eddies we can find? We have the loop current frontal eddies, these intra-thermocline, smaller scale eddies, and also we have these loop current frontal eddies. They are cyclonic eddies. They generate many times here, north of the Yucatan Peninsula, and they propagate on the edges of the loop current. Here what I show is a very important processes where these eddies are involved. That it's a process that we call loop current necking. So the loop current necking is that two loop current frontal eddies work together on both sides, on the Yucatan side and on Florida side, and they work together to shrink the loop current, and ultimately they're gonna merge, form a larger cyclonic eddy, and this loop current frontal eddy is gonna be released. So they are involved on the shedding of these large loop current eddies. So they are pretty important. And another important thing or role of these smaller cyclonic eddies is that they contain, well, we thought that they contain, this is a work of Rudnick et al., 2015. They show TS diagrams inside loop current frontal eddies and inside loop current eddies, anticyclonic on red, cyclonic on blue. And what we see is that the cyclonic, these small loop current frontal eddies have Gulf common waters. So what we thought is that they have Gulf common waters because they are formed outside the loop current. They are formed inside the Gulf of Mexico typical waters. So they must have these waters. But we did this section of one of the loop current eddies. This is the loop current eddy, the contours of the periphery of the loop current eddy, the trajectory of the glider. This is the loop current. So in this section, we observed that this eddy contains subtropical underwater, not Gulf common water. This was a very striking finding because, well, the publication said that they contain Gulf common water. We don't know how these loop current frontal eddies can incorporate the waters from the Caribbean. We are investigating on that. But what is sure is that we can find this kind of eddies with Caribbean waters also. These small eddies have also very strong anomalies, but negative anomalies, because there are cyclones and the isopignals are upward. So there are 5 degrees of temperature anomaly and about 0.5 PSU of salinity anomaly. And here I want to highlight that maybe these eddies, we thought that they could not contribute to heat and salt budget because they contain Gulf common water. But if they contain subtropical underwater, why not they could contribute to the heat and salt budget in the Gulf of Mexico? This eddy that we sampled on mission 12 propagate together with a loop current eddy, forming a dipole, and propagate towards the Campeche Bay. This is the Campeche Bay, and there merge to a local cyclonic eddy to form a large cyclonic eddy. We sampled this large cyclonic eddy on mission 13th and found that contained also subtropical underwater. So loop current frontal eddies must contribute to the heat and salt budget in the Gulf of Mexico. Don't know what happened. Yeah, okay. So I keep going. So we do not see only mesoscale and submesoscale. Here I'm going to show some observations on smaller scale. So the glider, it's also, we can also study submesoscale processes because we get these 2 kilometers, 3 kilometers horizontal resolution. We are on the limit of the submesoscale. But here I want to highlight that we can use also these gliders to study small scale processes. This process we call layering. On the plot, this plot on the left side, I show the high pass filter SPICE. What's the SPICE? The SPICE is the contribution of the salinity anomaly to density anomaly minus the contribution of temperature anomaly to density anomaly. So what indicates this variable, the SPICE? The SPICE indicates if there is or not compensation, if salinity is compensated or not with temperature. So when there is a very strong compensation, we have very large SPICE. This is very nicely showed in these vertical profiles, where I show here the contributions of salinity anomaly and temperature anomaly, and we see that they compensate each other. So this is reflected with high SPICE. So high SPICE means strong thermoline compensation. So these layers are regions with very large thermoline compensation, are layers that extend horizontally tens of kilometers, and vertically they have scales of few meters. So we can say that there are small scale structures on temperature and salinity. And where these regions develop, these layers develop near these regions, the velocity course of the eddy. This is the velocity course of the loop current eddy Poseidon. This is the section of loop current eddy Poseidon, geostrophic velocity. So here we have very strong vertical shear on this region. So we believe that these layers are related to the vertical shear of the loop current eddy. And to show that, we did a QG modeling. On the left side, I'm showing the temperature, high pass filter temperature on gray scale. And on the red lines and blue lines indicate the geostrophic stream function and potential density. And here I want to highlight that these layers are not aligned with the isopignals. They are aligned with the stream function. So this is very important because this indicates that these layers are dynamical, are generated by some dynamical process. And we believe that this process is the vertical shear. We did this QG modeling. This is a three-dimensional vertical shear-lit eddy, and we put some columns of tracers, and what we see is that there is going to be a differential advection of the tracers by the differential velocity profile. So we can see here how we can simulate the formation of these layers with this QG model. So just with a shear vertical profile, no? So to finish, I'm going to talk a little bit about some relevant observations on chlorophyll that we get also with our gliders. We have many profiles of chlorophyll backscatter. So I wanted to share with you. I know that in this institute there is people that works with phytoplankton and fluorescence. So here I show the distribution of surface chlorophyll from satellite virs, and pretty much the Gulf of Mexico, it's oligotrophic. I don't want to say oligotrophic because this is not biomass, it's just pigments, no? A concentration of pigment. So well, I'm gonna say there is a lot of pigment instead than biomass. But we see high concentration of chlorophyll on the coast, and in the middle of the Gulf of Mexico, it's a very low chlorophyll region. Especially you can see this darker region that is the loop current eddy Poseidon. So Poseidon, it's a very oligotrophic eddy. Inside the loop current eddies, typically we have very low concentration of pigments. But it's not the case. Well, we'll see that there are some events of enhancement of chlorophyll inside these eddies. First, I want to show a climatology of the vertical profile of chlorophyll using all the glider missions. And what I do, it's average all the profiles of chlorophyll during spring, summer, winter, and fall. And the different colors indicate the different seasons. The standard deviation, it's on shade on color. And I want to highlight two things. The first thing is that there is a DCM, a deep chlorophyll maximum, that is centered around 100 meters depth. And the second feature I want to highlight is that it's the contrast between these two profiles, the autumn vertical profile of chlorophyll on yellow and the winter vertical profile on blue. And we see very structural differences in terms of the depth. It's shallower on winter, the depth of the DCM, and also we see enhancement of chlorophyll near surface in winter. So what's the physical mechanism for that? We have some hints on this because we know that the winds are very important during winter that generate gravitational instabilities. No? So let's see first summer conditions. This is again loop current eddy Poseidon, two sections, first section, second section. This is stratification or just the vertical derivative of the potential density anomaly. Red colors indicate high stratification. Again, we see the two thermoclines, very stratified in summer. And the chlorophyll, it follows pretty much this isopycnal. That's isopycnal of 1,024 kilogram meter cubic. They follow very nicely inside the eddy. There is a very strong linear correlation between this isopycnal and the depth of the DCM, but this relationship it's broken in the periphery. In the periphery of the eddies, there is no relationship between density and chlorophyll. What happens in winter? Winter, the story is much different. The surface stratification, it's not anymore because the winds erode this seasonal thermocline, and then the mixed layer reach very deep levels, about 150 meter depth in winter related to the 40 meter depth in summer. So chlorophyll also, very different distribution of chlorophyll. Yeah, we don't see anymore this deep chlorophyll maximum, and all the chlorophyll is distributed within the mixed layer. We see some variability, the diurnal variability or high frequency variability, and we also see a low frequency variability. So this looks like there is some forcing, and can be a physical forcing. Or I'm gonna just talk about the physical forcing. I know that there are probably metabolic forcings or biological forcings, but I'm gonna talk at what we believe that produce these distributions of chlorophyll in winter. So what we believe that the responsible for these enhancements of chlorophyll in winter are the winds, again. So upper layer is depth average chlorophyll for the whole year inside the loop current Eddy Poseidon. Middle panel is surface chlorophyll A, and the bottom panel is the wind above 10 meters of the sea surface on two buoys, the National Data Buoy Center, these NOAA buoys that are in the Gulf of Mexico. And then I highlight that there are events of strong winds in winter that are above 10 meters per second, and at that period it's when we see this enhancement of surface chlorophyll, and also we see this enhancement of depth average chlorophyll. And you can see there is a very nice correspondence between the peaks of wind and the peaks of chlorophyll. So it arrives a front called front that we call nortes. These are fronts that come from Louisiana, Texas, and they propagate through the Gulf of Mexico. And we can see that gets one front, and few days later we have a maximum, then gets another front, and few days later we get another maximum of chlorophyll. So we believe that these maximums or enhancements of chlorophylls are related to the entrainment of nutrients by the convection in winter. And to show that, I did some spectral analysis, and on the left side I show the spectrum for the wind data on these two buoys, and we see there are several peaks at different periods. We have strong peaks at 18 days, 10 days, 7 days, and these are typical periods of nortes. More or less we get a norte every week in the Gulf of Mexico in autumn and winter. And also we get this sea breeze, daily peak. If we do the same, a power spectral density, but for the integrated chlorophyll, for the plot I showed before, for the one on the top, I compute the spectrum, and I see that also we have peaks at 24 hours, 7, 8 hours, and 10 days, and 10 days. So there is a very nice correspondence. We believe that this variability of the chlorophyll is related to the passage of these cold fronts that inject nutrients into the photic layer and generate a new production and blooms of phytoplankton. No? So is this possible? The wind can reach the high concentration of nutrients. Here I show, this is not mine, this is from Victor Camacho. It's a guy that works with chemistry in the Gulf of Mexico, and they were able to collect a typical vertical profile of nutrients inside eddies. Inside cyclonic eddies is on blue, inside anticyclonic eddies is on red, and outside the eddies is on black. So what we see is that in the deep chlorophyll maximum layer, inside cyclonic eddies we have a lot of nutrients, well, a lot of nitrates. It's the blue line. And inside anticyclonic eddies, there is a very low concentration of nutrients. But in winter, we can reach depths of 150 meters. So we believe that maybe you can, the biologists here, they can help me with that, but we believe that the northern winds are able to entrain nitrates from this Nutricline and inject into the photic layer and create phytoplankton blooms. And I think it's all that. I have many other slides, but I think I'm going to finish here. This is just the website of our group. You can check this website, but you can check all our data. You can visualize all the data. These 19 missions are not public yet, but the next missions, now we are on the mission 21, and the 20 and the 21, the data is going to be public. So you can check this page and navigate over there, and you can find data. And well, if you want, you're welcome to check this website. And thank you very much. And if you have any question, I can answer or try to answer.
Thank you. It's a very nice talk. I have just one question for you. Is what is the role, if it happened that you had the occasion to see it, of the hurricanes on this structure? Did you find anyone?
Yeah, I did not. Yeah, we did not. Probably we have some mission of a glider beneath a hurricane, because there are no ships in the Gulf of Mexico when a hurricane's approach. But the gliders, it's one cool thing that we can have the glider just beneath a hurricane. We have some observations, but we did not analyze. I did 2 works before I started with the gliders, with some moorings. We had 3 moorings in the Gulf of Mexico, and Hurricane Ida in 2008 and Hurricane Ike in Ida was 2009, and Hurricane Ike in 2008 were hurricanes category 4 and 5. And I have 2 publications regarding the ocean response to hurricanes. And pretty much what we see is that the passage of the hurricane leaves a wake of waves and on inertial frequency. And these waves, when interact with anticyclonic vorticity, are believed, well, we observed that, they propagate downwards. So what we observed is that very strong packets of near inertial waves propagating downwards to the bottom of the eddy, down to 900,000 meters depth, and they get trapped there. It's a phenomenon we call wave trapping, and it's because it's a change of vorticity, but usually they trapped inside anticyclonic anomalies. So you need vorticity, negative vertical vorticity. Yeah. For positive vorticity, when propagate over cyclones, the packets of near inertial waves get out of the eddy and don't propagate on the bottom. So we can, there is this paper that they call inertial chimney, como chimenea inercial. So the anticyclonic eddies are like inertial chimneys, and they focus the wave energy towards the bottom. Now we have a project for October 2022, and we're going to do simultaneous measurements with microstructure down to 2,000 meter depth to try to capture the mixing. Because with the moorings I could not measure mixing. I just observed the waves propagating, but I couldn't not say nothing about mixing. And we know that internal waves are very important on the mixing the interior ocean. So it's a very interesting process, yeah.
And this has any impact on temperature and salinity because of the latent heat exchanges or water on top of the
yeah, field. This is the second aspect. It's the thermal response. We have the current response in form of inertial waves, and then we have the thermal response. And the thermal response, when it lets a cold wake. A cold wake, it's a wake of cold water, and then the hurricane gets intensified. Because remove the heat from the ocean, gets intensified, and the ocean gets colder. So the anticyclonic eddies are food for the hurricane. So now it's very important for us to measure with the gliders on real time, because we're getting information on real time. So now NOAA and all the hurricane forecasters are asking for the data all the time. Provide us data of temperature on real time, because we can compute the ocean heat content, and knowing the ocean heat content, you can use to estimate the intensity of the hurricane and the best track to know where it's going. No? The NASA or NOAA, they want to know where the hurricane goes and what is its intensity. So this is very important. The ocean heat content and the loop current eddies are huge anomalies, warm core rings, with 9 degrees of temperature anomaly. They're huge, no? Huge amount of heat. Yeah.
Okay, thank you very much. And a small,
go ahead.
Just a comment. I think that there is an error in one of the slides that you mentioned that the square Broom by Sala is negative. Just a comment that something is not.
No, yeah, it can be negative.
Yes.
Yeah.
Oh.
Yeah, because
it's not a real number.
No, but the squared has no la raíz, no? The squared, it has not the ¿cómo llamas la raíz cuadrada? There is no square root on the squared Broom by Sala. The square root is on the Broom by Sala, not on the squared Broom by Sala. Squared Broom by Sala, yeah. When squared Broom by Sala is negative, it's gravitational unstable, the water column. Yeah. Yeah, no, well, I can show you the equation, but yeah, can be negative, yeah. It's not a complex number.
In that case, it cannot be defined as n squared. N squared is negative, but n is a complex number.
Yeah, n it's a complex, but not n squared.
No, of course. Yeah.
N squared can be negative. N cannot be negative, but n squared, yes. Yeah. Well.
Any questions?
Thank you. Thank you very much. Just a few comments. Very interesting. I'm so happy that we'll collaborate in this
new project,
Antarctic project, hopefully, and we'll have your expertise on gliders. Just a few comments. Maybe it will be very interesting to also look at the integrated chlorophyll, integrated heat, integrated salinity, and make a spectral analysis of those quantities, no? And also see how it changes in time and make the spectral analysis. Because if you are looking only at the surface values, for example, of chlorophyll, or then you have only an indicator of I don't know if you look at the integrated values, no? You have this depth average, for example. This doesn't tell you how much chlorophyll is there, so you don't know if it's really growing, it's being enhanced because of nutrient injection, or is really just being distributed vertically. You know? So I would try to at least define some mixed layer value, or by some criteria, what is the depth of the mixed layer, and then integrate the chlorophyll in the mixed layer, maybe incorporating the thermocline as well, no? But that might be indicative, no, of what's actually happening, no? And if you have oxygen also in the glider, maybe it will be worthwhile also, because that will give you indicators of primary production, no? Oxygen
the AOU, no?
Yeah,
the available oxygen.
Yeah, or maybe, yeah, of course, oxygen, you are always exchanging oxygen with the atmosphere, no? But if you look at, for example, oxygen in the mixed layer, in the thermocline, maybe that that's an additional hint of what's the primary production there, no? Because of this nutrient injection that you mentioned. No?
Yeah, actually, it's a very good point. The first point you highlighted, there is a work on 2019. This is not published, so it's not yet approved. Well, I mean, it's not per review. So there is a previous work that stated what you say, that there is no new production, it's just redistribution. So they with BioArgos, it's a French guy, and they do that. They see that the chlorophyll is distributed, but it's the same one it was on the chlorophyll maximum. But it's just the convective cells just redistribute the chlorophyll, but there is no growing. No, that was the main result of this work. But we tried to say that there is new production, but I need to check that.
The images you showed just before or after this were really extraordinary. No, just yes, this one for example. These are impressive. No, another comment you mentioned this in this case this anticyclone with the cyclonic gyres on the surrounding. This is something also you see in the Sapiola gyre, no? In the Sapiola gyre, in the South Atlantic, you have this permanent anticyclonic with cyclonic, and there were also some Argo floats deployed there in the last May, April, so might be also interesting. No? And a final comment is this. In here, for example, when you look at stratification, I see no negative values. I mean, the stratification is always positive, but so it strikes me when you mention that in some instances up to 70% of the water column is unstable. This is something that if I were a reviewer, I wouldn't believe at all. So I will be very critical on that. And particularly if this instability stays for a few, maybe a few hours, hardly I would believe it. But for a few days, I would not believe it. I would be very critical on that. So I might be wrong, of course, no? But my impression is that in here you don't have instability. When you say 70%, this is a very, I wonder if it's a problem with the synchronity between the salinity and temperature. Maybe there's some lag. Just suggest to review that. No?
Well, we believe are true these inversions of density. We believe. Huh?
Yeah, there might be a few ones. We've seen them very rarely in hydrographic data. I mean, you don't, and you have very high resolution vertical. Yeah. You have several values every meter. But this is something really very extraordinary, no? And this is my feeling is that it's something that is maybe happening and then rapidly disappears. It convects. It cannot stay there. No. Yeah. Of course, you have this injection from the lateral eddies with this shear that you are mentioning. No, see, this probably brings perhaps some of these instabilities. But I find it hard that they stay for days. No, but maybe I'm wrong.
It's not that they are not staying for days. It's the gravitational instabilities are by events. It's not that the whole eddy is sinking, no? It's just that you see the front, it passes, it cools down the sea surface and gets higher density, and you have this overturning. So what we see are these overturnings, but it's not that the whole eddy is overturning. The overturning it's in small cells, and it's a discrete phenomena. So what we see that are discrete events of inversions of density. If you see the density profile, it's clearly decreasing with depth, no? The density. But it's not just one pixel. There are a lot of observations. It's not one observation. It's many observations. So this is I mean, it's very known in the Gulf of Mexico that there is gravitational instabilities in winter. For that, we do not have problems. Actually, this work is in revision, and they agree with the gravitational instabilities. They are fighting more for the symmetric instabilities. The gravitational, they accept it for the moment. We don't have problems with the gravitational, but the symmetric instabilities, they say that with the glider, we're not able to measure the horizontal gradients accurately, but vertical gradients, yes. The glider, it's very, very good to measure vertical gradients of density, or measure vertical profiles, high-resolution vertical profiles of density. But it's not that all the time it's unstable. No, it's by events. This gets this northern wind, cold wind. There is a event of gravitational instability, it stops. There is another northern wind, another event of gravitational instability, and it's by events.
But in one of the slides you showed before this one, you showed these 70% values of
the water column.
That lasted for very long. No, this is, as you say, this is one process of convection, and this rapidly has to disappear. Maybe the shear, the vertical shear, would last longer, in my view. If you have vertical shear, that can help it keep on stable for longer, but the vertical convection should not last very long.
Yeah, but this is, you need to realize that this is a year. So it looks like everything it's continuous, but these are events. These are events, no? It's not that this is continuous, but it's the scale, the horizontal scale, the time scale, it compresses the plot. But it's not that all the time we have. If you see there are white patches, and this is because there is strong stratification here. Sometimes there is strong stratification, and we don't get these unstable profiles. But these unstable profiles start when the depth of the mixed layer start to deepening, no? Then start the gravitational instabilities, and during winter it's all the time by events, but we found these events of gravitational instabilities. Yeah. I don't know.
Thank you very much.
Yeah, you're welcome.
Thank you, Enric. Have you ever measured horizontal gradients of PV? Have you found any inversion in the horizontal gradient of potential vorticity?
Yeah, the inversions of potential vorticity, well, we have this criteria, Hoskins, that says when F by potential vorticity is negative, we have it's a necessary condition, but not sufficient, no? But at least it's an indicative of possibility of symmetric instabilities, and there are very few events at the periphery of the eddy. And these events of low potential vorticity, we believe are related to down-from winds. I don't know if you heard about down-from winds. It's winds blowing on the direction of the frontal jet. So what happens is that the Ekman transport takes dense water from the dense side to the light side and then sinks on the light side. So we have this kind of overturning due to down-from winds on the periphery of the eddies. But these ones, we believe that Thomas, you maybe know Mariona Thomas, it's our reviewer, and it's being very, very tough. And he said, no, you're not seeing symmetric instabilities, gravitational okay, but symmetric, they don't believe that we were able to observe these inversions of potential.
That's the quasi-geostrophic PV. It's an anomaly.
Yeah, this is an approximation. Yeah, it's a geostrophic PV.
Dominated by the stratification or dominated by the
stratification?
How percent? 90% is stratification?
Yeah, totally. Yeah, mostly 80-90% of the PV it's controlled by stratification. Okay. Yeah.
What's the resolution of the glider, the lateral resolution?
Lateral resolution we have between 2 kilometers, 5 kilometers. The problem was we start to do optimal interpolation to get the gradients. So if you use a very large Gaussian function to filter the data during the interpolation, you smooth the gradients. So what we found that we couldn't use optimal interpolations to study this kind of instabilities, and we don't interpolate. We just do a binning of the profiles, and then we interpolate linearly to try to don't touch much the profiles and try to get accurate horizontal gradients of buoyancy. because for PV, we need these horizontal gradients of buoyancy. That this is what we solve. It's our weak, how you say? Weakness, no? Because vertically we profile very, very good, but horizontally we have this limitation.
Yeah, I believe if you increase the resolution on the lateral dimension, you're going to resolve symmetric instability. But you have to go down like 1 kilometer resolution.
Well, LES, no?
Yeah. But
A large Eddy
it's also common,
simulation.
like I believe like these, where you get static instabilities with negative n square, it's because you have a turbulent mixed layer there, right? And I also get that on the simulations. I get like inversions in density because it's all turbulent, that layer. And also like some symmetric instabilities there, but yeah, so. And also, what's the green point?
Yeah, the green, I don't want it to talk about
Okay.
green. But no, because we use a Leif-Thomas method to classify the instabilities. I don't know your use, it's the Phi-Richardson gradient. It's the angle,
Yeah.
He defines angles, and between the angles you can classify between gravitational instability, symmetric. And there is this mixed gravitational symmetric instabilities, that there are instabilities where n squared it's negative, but PV also it's negative. Or you have n squared positive and PV negative. So you have different kind of instabilities, and we use this method. And using this method, we get, actually these yellow ones are mixed gravitational symmetric instabilities, but I said gravitational instabilities, and the green ones are the ones that are pure gravitational, but using not the n squared minus 0, using the method of Thomas. It's a kind of, it's when the Phi-Richardson gradient is less than 135 degrees. But
Yeah, but I think that definition also assumes geostrophy. So,
this one.
like the one for the angles you were mentioning.
Leif-Thomas not, because he does that on a LES of the Gulf Stream.
Okay, yeah, I
So-
don't know
so-
which one, but he has also like a definition on the angles, and in their definitions he assumes geostrophy, but I don't know if he has done more work without assuming that.
Yeah, our problem is that the only we can measure is geostrophy, so it's a little weird that we can to solve a geostrophic instabilities with geostrophy, because but we're not solving the geostrophic instabilities, but we're telling what are the conditions of the water susceptible to this kind of instabilities. I'm not saying here there are gravitational instabilities. I'm saying here the conditions of the water column are conductive of instabilities, because the reviewer said that no, these are not instabilities. You need to really highlight that are the conditions of the water column for these instabilities, but you're not solving the instabilities. So yeah, I agree that we're just checking some conditions, mixed layer with PV negative, mixed layer with n squared negative, some conditions that tell us about the possibility of development of instabilities.
Yeah, I mean, it's very hard to sample this, so it's
Yeah,
already
you need
great
this
you get
1
this.
meter resolution. Yeah.
Okay. Is there any questions? No more questions? Well, thank you very much,
Thank you.
Enric, for coming and telling us the very
Thank you for inviting me.
interested.
Yeah,
All right.
I'm at home. Thank you.